Okay, the third objective, we will look at applied problems using exponential equations. And the first application we'll look at, it considers half-life. And half-lives of different substances are, vary. And how this is helpful in science is knowing the half-life of some element helps us calculate the amount remaining after a specified time. So here we have the half-life formula. We have A of T equals A naught, or A with that little zero means A initial value, 1/2 raised to T over H. So what A with the A initial is the amount of the substance that is initially present. H is going to be your half-life. Now that's the amount of time. It could be years, it could be minutes, but if it's in years, it's the amount of years that will take the substance to be reduced by half. T is your time period, and A of T is the final amount, or the amount of the substance that's there at time T. So we have here uranium-235. It has a very long half-life of 703,800,000 years. Okay, let's calculate how long it will take a 1,000 gram sample to decay to 900 grams. Right, so we have, well, first, actually, let's rewrite the formula. So we have A of T equals A initial, 1/2 T over H. And then determine what are we given. So we're given that half-life is 703,800,000 years. So that's our H value. Then we are given that we're starting with 1,000 grams. So that's our A initial. And we want to find how long it takes it to go down to 900 grams. So that's your final A value. So we'll replace that with A of T, 900 grams. It looks like we're solving for T, right? Because it says how long. Okay, so we have all the given written down. So let's use this formula and substitute what we have. So A of T, we have 900. Initial A is 1,000. 1/2 T, we don't know. H is that big number, 703,800,000 miles. Okay, first try to isolate your exponential term, your base, it's the 1/2. And so we need to get rid of this 1,000 first. So get rid of the 1,000. We can do that by dividing both sides to 1 by 1,000. 900 divided by 1,000, we can simplify that to 0.9. Then we're left with 1/2 raised to T over that big number again, 703,800,000. Okay, now we're going to take the ln of both sides. So we do ln of 0.9 and ln of 1/2. It's getting a little tedious writing all these numbers out with 703,800,000. And now, right, because there's an ln, we can use a power rule to bring that expression down. So we have ln of 0.9 is equal to T over 703,800,000 miles of ln 1/2. All right. Actually, let's change that 1/2 to a decimal. It really doesn't matter, but just to keep it consistent with the 0.9, let's make that a decimal. I'm trying to grab my eraser here. And we have 0.5. Okay, now to solve for T, we would have to divide both sides by ln of 0.5. Okay, so if we divide both sides by ln of 0.5, that'll help us get rid of this 0.5 here. We have ln of 0.9 divided by ln of 0.5 equal to t over that big number again. And finally, if we multiply both sides by this huge number, we can isolate t and find out how many years it takes to break that down to 900 grams. 703, 800,000. So t is isolated. Let's plug that into the calculator. We have t. Head over to our calculator now. Okay, so we have here ln of 0.9 divided by ln of 0.5, and we multiply that by 703, 800,000. And we get that big number, 106. I think that's 1,979,777 years. Very long time. Okay, so t is equal to 106,979,777 years. So it takes that long just for 100 grams to, for 1,000 grams to decay to 900 grams. Okay, let's look at one more problem together. Newton's law of cooling also uses an exponential equation. This is a formula where it takes an object at time t and see how it cools down based on the surrounding temperature. So we have this formula here, t equals t sub s plus t initial minus t sub s. We have e and then raised to negative kt, where you have this t sub s is the temperature of the surrounding environment, and t initial is the beginning temperature, and you have k is the cooling rate, because all objects have different cooling rates. So we have a cup of coffee that's super hot, freshly made. It's 180 degrees, and after 2 minutes in a room, 70 degrees, so that's the coffee has cooled down to 165 degrees. We want to calculate K, its cooling rate. All right, so let's again start by writing down what we are given. So our T initial temperature looks like we're starting at 100 degrees. So that's the initial temperature of the coffee. And then we're also given after 2 minutes, so T is 2 minutes. The room temperature, that's our surrounding temperature. So TS is 70 degrees. And our temperature that's given 165, that's our regular T. That's the temperature of an object at that time after 2 minutes. So that's 165. Okay, so I think we've listed everything that's given. Let's put it in the formula. So writing down the formula here, T equals T sub S plus the T initial minus T sub S, E raised to the negative KT. Right, so T is 165, T with the surrounding temperature 70, the initial temperature is 180, minus the surrounding temperature again, 70, E negative K with the T, the time, the little t being 2, lots of t, so we have to make sure we don't get confused between all the different t's. The idea again is to isolate the exponential term. So we have to, let's try to simplify as much as we can. First thing, well, let's get the 180. We can write that as 110. So let's do that first. 165 equals 70 plus 110 e to negative 2k. So we can subtract 70 first and get 95 equals 110 e to negative 2k. And now, let's see, we can now divide by 110. We have 95 over 110 equals e negative 2. Now at this point, we're going to do ln to both sides. We get ln of 95 over 110, ln of e negative 2k. And of course, the ln of e, that was one of the equations that we can use to simplify. We have ln of 95, 110 is equal to negative 2k. We're almost done. We can now divide both sides by negative 2. And k is equal to ln. I'm running out of space here. Maybe I'll write it here. I'm going to take this all the way here. K is equal to ln of 95 over 110 divided by negative 2. Once we put that in the calculator, we have 0.0733 as our cooling rate. Okay, so number 3, we have a different type of problem looking at atmospheric pressure. We'll actually also do this one together in class, but it might be good to just try to solve it on your own before we meet for class. Okay, I hope this gave you a better understanding of exponential equations. Again, if you have questions, feel free to reach out to your professor.